Hello and welcome back. The board again is full. We're going to go over it slowly. We're going to apply the concepts that we've been learning in fluid statics to another problem from your OpenStax textbook 1142. So just summarizing again up here on the top, we are dealing with fluid statics. We need to be able to work with pressure, which is force divided by area. That's newtons per meter squared or a Pascal. The three different types of pressure are gauge pressure, atmospheric pressure, and absolute or total pressure. Density is mass divided by volume. The buoyant force is the force an object experiences when it is submerged or partially submerged in a fluid that is in a gravitational field. That buoyant force is the density of fluid times the acceleration due to Earth's gravity times the volume of the object. And be careful here, that volume of the object is just the submerged part of the object's volume. And of course, the buoyant force is also equal to the weight of the displaced fluid. And this is actually Archimedes' principle we've been using, but not formally named as Archimedes' principle. But now you know that it is known as Archimedes' principle. Archimedes' principle says that an object that is submerged or partially submerged in a fluid experiences a force due to that submersion that is equal to the weight of the displaced fluid. So there we go. We're going to go ahead and apply this now to 1142 from your OpenStax textbook that reads as the following. Archimedes' principle can be used to calculate the density of the fluid as well as that of a solid. Suppose a chunk of iron with a mass of 390.0 grams in air is found to have an apparent mass of 350.5 grams when it is completely submerged in an unknown fluid. A, what mass of fluid does the iron displace? B, what is the volume of the iron using its density given in table 11.1? And C, calculate the fluid's density and identify it. So I've gone and looked up the density of iron. It's 7,800 kilograms per meter cubed. You can look that up in the textbook. And I have also written down the three things that it is that we seek. So we want to know what is the mass of the displaced fluid. It's very common to just write this as MDis. Dis stands for displaced. VI is the volume of the iron. And rho question mark is the density of the unknown fluid. And then we want to identify what it is from table 11.1, where some common densities are listed. So I've drawn a couple of pictures. One is the iron on a scale that is giving you its mass in air. And then I've drawn a picture of that same chunk of iron now completely submerged in a fluid and on a scale that rests at the bottom of that fluid that's giving you the apparent mass. That is the mass reading of the iron sitting on top of the scale. You see it's reduced when it is inside of a fluid. So this bottom level of fluid is the fluid level before the iron was put in. And then when we put the iron in, the fluid level rises up until the iron is completely submerged, and that new fluid level now is this upper line right here. And notice that this shaded area in between is the mass of the displaced fluid. So that's how much fluid had to get out of the way for that iron to be sitting in the fluid. So the first picture is going to give us a free body diagram that says that the normal force up, and we can read the normal force because this mass times the acceleration due to Earth's gravity is the normal force, is going to be equal to the mass of the object. In this case, that's the mass of the iron times the acceleration due to Earth's gravity. So we can write Newton's second law from this free body diagram. Static equilibrium means the force is up equals the force is down, and there it is. Now we have the object that is in a fluid, so we still have the same force of gravity down on the object. The Earth is still pulling on all the molecules that make up the iron. But we now have two forces upward. We have the support force being supplied by the scale, and we also have the buoyant force supplied by the fluid that the iron is submerged in, and that fluid has a density that we don't know yet. Writing down Newton's second law, the forces up must equal the forces down to have static equilibrium. So Fm prime plus Fb must be equal to the mass of the object, which is the iron in this case. Mo is equal to mass of iron times the acceleration due to Earth's gravity. But Mog is the same as the normal force when the object is outside the fluid. So notice that the normal force being supplied by the scale in the fluid, I'm giving a prime sign to distinguish it from the normal force the iron experiences outside of the fluid. So I'm substituting M sub Og as Fn using this equation, and that allows me now to solve for the buoyant force in terms of the difference between the normal force outside of the fluid and the normal force inside of the fluid. So when I plug numbers in and put things in standard units, because this is in grams, these two scale measurements are in grams, so I need to multiply by the acceleration due to Earth's gravity, I am able to find a buoyant force, which is the weight of the displaced fluid. But we want the mass of the displaced fluid. So if I take the weight of the displaced fluid and I divide by the acceleration due to Earth's gravity, I now get the mass of the displaced fluid. And I went ahead and put it in grams. So 39.5 grams of this unknown density fluid is being displaced in order for the iron to sit there. Part B now, we want to find the volume of the iron. So we're going to use our density volume mass relationship, and we're going to rearrange it solving for volume. So volume is mass divided by density. So if I want to find the volume of the iron, then I need to take the mass of the iron and I need to multiply it by divide it by the density of the iron. So the mass of the iron is the mass of our object in this case. That's the subscript I'm using. I just chose M sub O. I could have used M sub I all along the way, but I didn't. So I'm substituting in M sub O to make it clear that that's what we're talking about, divided by the density of the iron. And when I put the mass of the iron in standard units divided by its density, I come up with 50.0 times 10 to the minus 6. And that units, kilograms cancels, and meters cubed in the denominator flips up into the numerator, and it's meters cubed. And putting it in a unit that maybe we get a little bit more flavor for the size of it, I'm going to go ahead and convert it to centimeters cubed. So I need to multiply by a ratio whose value is 1, and I know there's 100 centimeters in 1 meter, and I want to get rid of the meters cubed, so I'm going to put the centimeters in the numerator and the meters in the denominator. And if I multiply by this ratio only once, I'm only going to cancel 1 unit of meter, so I need to multiply by that ratio 3 times, or I can just cube it. Either one that makes more sense to you, use that. So when I perform this operation, I get 50.0 centimeters cubed. So there you go. That's part B. That gives us the volume of the iron. And then in part C, we want to know what is the density of this fluid. So we go back and use this equation, right? That's where the density of the fluid is sitting. It's right there in that equation for the buoyant force. So the buoyant force is equal to the density of the fluid times the acceleration due to Earth's gravity times the volume of the object, the part of the object that's submerged. In this case, the entire volume is submerged, so we're going to use the entire volume of the object, which is the iron. I've already given it the subscript sub I, so I can replace the volume of the object as V sub I to be consistent with all the other work here. So this is the density of fluid, acceleration due to Earth's gravity, times the volume of the iron. Rearranging now for the density of the fluid, I get the buoyant force divided by the acceleration due to Earth's gravity times the volume of the iron. And now plugging those in, I found the buoyant force earlier as 0.3871 newtons. Acceleration due to Earth's gravity, and now the volume of the iron. I want to be careful to use standard units for that volume, so there it is right there. And when I work out these numbers, I get 790 kilograms per meter cubed. And so when I go back and look at table 11.1, I find that that value is the value for ethyl alcohol. So this iron is being submerged in ethyl alcohol to experience a buoyant force of 0.3871 newtons and have a mass of the ethyl alcohol that had to get out of the way of 39.5 grams. So that is an application of Archimedes' principle to 1142 from your text. So we'll see you next time. Thank you.